Alright, making a live video. Yeah. Why, I'm not too sure. But I'm doing it anyway. See if it ever comes up live. There it is. Okay. Gotta do a little bit of this crap and such. So, commenters. Yes, I'll actually be interested in people's input, for some of this. Because, wait, what do you do about crazy fucks on the internet? And, physicists who are crazy fucks. I mean, they want to get into some sort of personal confrontation, because you don't agree with their physics. And you might even say they're morons and idiots. That means you should invade people's private life in all kinds of silly and stupid ways. And no, I don't think it should. Yeah, I don't think that's what it should mean. Look, the fact that he made a stupid rag page about me, isn't at all interesting. But the fact that he's, this whole doxing thing just pisses me off, because this is really easy to understand. I don't live in my house. I live in somebody else's house. And so it's their security, you're jeopardizing. And it's just like, fuck. And it's a woman besides, which makes it okay. It's a little more vulnerable. It's something you don't really mess with. You don't fuck with other people related to somebody else. You don't do that. And the fact that this physicist can't even understand that, that he would have to resort to this bullshit in the first place. You're just like, what the fuck? But this is apparently his character. Okay, so, his videos are all over the place. He's got fucking video game. This is a physics professor. Video games. Then teaching people how to make chloroform and explosives. And you're saying, what the fuck are you putting that online for? Like there aren't enough, you don't think there's enough crazy people in the world and you just want to facilitate their functionality? You want to make them more functional in being crazy? Who the fuck needs chloroform? What the fuck would you use it for exactly? What would somebody in their own home need to use chloroform for? I can't come up with any good reasons. Yeah, none. Except to do something malicious and nasty and, whatever his name was. The guy famous for doing that. We didn't use chloroform, some other drug. But anyway, Bill Cosby, yeah. Oh, fuck. Crazy world, really. Just so fucking silly that you have to put up with this horse shit from these loonies. So anyway, I did put up my own page about him. Okay, I started one anyway. But I'm not at all interested in this personal shit. I want to argue physics. So the lunatic keeps emailing me. I don't respond to his emails. He just keeps doing it. And you're just saying, obviously this is one of those things where apparently he's in love with me and he wants me to fuck him in the ass or something. And so he really needs my attention, because if he doesn't have my attention, he feels like he's not going to be able to, get what he wants, whatever the fuck that is. And it just doesn't make any sense at all. So he's a piano, he's a, whatever, you could call him a musical artist. He's made a couple of videos, got his family in them, which really doesn't make any sense if you're going to be online, fucking with other people's lives. That's a pretty dumb thing to do. And it's just, defacing someone else's art. His wife is a folk art. He's got a doctorate in some sort of folk art bullshit. Real garbage art, frankly. And he's he's abusing somebody else's artistic expression and then defacing it. And you're just like, did you check with your wife whether that's an ethical thing to do, is to deface somebody else's artwork? He has just no character at all. So the last email he sent me just today was, hey loser, Did I make you upset? You're so quiet lately. No, I'm still making physics videos, idiot, because I'm not really interested in you or your stupid petty little shit brain or your silly little fucktarded life or your plumpy wife or any of that shit. So just take all your bullshit elsewhere, fucktard. You can't make a physics argument. I'm not interested, shit for brain. I mean, this whole page is all this fake narrative that has nothing to do with the physics argument, that doesn't in any way illustrate it in any way. I mean, it's just, what the fuck from a physicist? This is, you don't expect it from, a professional, okay, who has a professional standing in a university. Now, it's not, he keeps saying University of Louisiana, and it's not that. It's Xavier University of Louisiana. Catholic, university. So you're even saying, ooh, I mean, that's sort of a taint on a scientist, but whatever. But obviously he doesn't share any of those Catholic values beyond being obsessed with penises. So I did appropriately adorn him, just because of his obsession. So, but I really don't. What is your alternative? What would you fight back or not? And again, it's this whole idea that he's plenty exposed. I mean, the very fact that people can't understand that dissidents face, a real threat from the public. Minority opinions, minority positions are always dangerous. And, not to appreciate that until you're the minority, you're just not thinking straight, fucktard. That you don't, that's a completely different position. And, maybe you can afford to put your name out there because you're not saying anything controversial. But go ahead and do something controversial, fucker. And then all of a sudden, maybe you're not going to feel so secure in what you've done. Make a political video, fucktard. Go ahead, do that. Something more bold than saying Tesla wasn't all that. Yeah, something bolder than that. So anyway, so it is weird. So I won't bother going on and on about it, but it is challenging to figure out how you respond to people who just don't get anything, who are really fucking just so goddamn silly and stupid, and think that, I don't care about your rag. Like I said, the only part I care about is the part where you threaten the security of other people connected to me. That's the part I can't find acceptable. And so if you want to provoke further action from me, I can take further action. I can get into your personal life, fucker, if that's what you want. All right? So just understand the position you're putting me in. I'm sure it's not that hard for me to write a letter to the whatever they call it, the person in charge of your university, asking some simple questions. Is this the kind of asshole that you think's a role model? Anyway, so just think about it, fucker. All right, anyway, it's just so disgusting. So I guess I will play a video by... So I am making the series of videos, obviously, on that aren't getting viewed much, which is, typical of YouTube. The 10-minute videos, 10-minute versions of the... basically all the little arguments you can make about how kinetic energy just doesn't fucking work. And what the hell am I looking for here? The right website. I know it's here somewhere. Y Newton. There we go. Alright. So nothing. Let's see. Click over here. What's in the chat? Cute cat. Yeah, oh yes, it's just in my notebook. My mouse pad. Waiting for a physicist to respond to the last 5 videos you made. They were to the point. Yeah, well, obviously they're not getting viewed, so that's part of the quandary, is how to get them interested. So I don't know whether I have to do another little email campaign or something, I guess. You know, it's just so irritating. But, you know, these are basic physics concepts, and the fact that you can't get any of these physicists to respond to what are there obviously there's issues that create what certainly appears like paradoxes in terms of what actually is conserved and what actually does work. You know, the next one I'm going to be making is probably the ballistic pendulum, or the the free momentum thing. Is just so obviously weird. I mean, the very idea that you have a concept where you have a closed system, and in that closed system, 1 second you have 200 joules, next second you have 100 joules, then you have 200 joules, then you have 100 joules of motion. You know, the very idea of unmotion or anti-motion or negative motion, I just don't get how somebody could actually believe in that, especially after I've made these arguments that, you know, you hit a bunch of pool balls and you have pool balls going in opposite directions. Do you subtract that motion from the total motion? Well, if you do, then you're not going to conserve the momentum. I mean, it's just, you're saying fucked. You know, these arguments deserve a response, and you know, the fact that they won't make one that doesn't include a bunch of insults and wasted time is just so fucking irritating. But yeah, that's life on Earth. Okay, so I gotta get over it. And so anyway, this is just a throwaway video. I just said, well, I don't feel like making the next video, so I'll just make a live video and decide what to do with the unpleasantness, created by the complete asshole who thinks invading people's personal life and personal hobbies and personal anything has anything to do with a physics argument, which it certainly doesn't. Alright, anyway, so let's see if we have enough proper volume here. His videos tend to be a little loud, but not this time. Yeah, it's not all the way up.
Second.
Alright, that might be enough. And this should be him. Alright, so this is Jason something or other, and used to work for NASA. Okay, I don't know in what capacity, but so Newton's second law. So this is really, it's just kind of funny because it says, okay, why Newton's second law is the foundation of physics, and it really isn't. It's the line drawn in the sand between Newton and Leibniz. Clearly, Newton believed twice the force, twice the motion, 3 times the force, 3 times the motion. He emphasized it right under the second law. So obviously he saw huge proportionality or correlation between force and motion. They're essentially equal each other, is frankly what he's basically saying. That force is momentum, and it causes momentum, and there's no v squared element. The velocity isn't increased non-proportionally to the force. It's proportional to the force, equal to the force. So this is the big lie of physics, that somehow they're going to convert Newton into a Leibnizian. So Newton's worst enemy in life, they're recklessly and with complete disregard to the status Newton should have, they're going to fucking plagiarize Newton and distort it. They're going to pervert Newton's concepts into somebody else's concepts, which is a pretty disgusting thing to do. Clearly Newton didn't say F equals MA, and he clearly didn't say 9.8 meters per second squared. He didn't say those things. That's words they've put in Newton's mouth that are Leibniz's concepts, not Newton's.
Law of motion, and this is part 1. So this is, without a doubt, one of the most important lessons you'll ever watch and learn about in physics. There's an old joke that if you know Newton's second law of motion, you can solve almost any physics problem. It really
So I think I've played this before. Sounds pretty familiar to me anyway. But we'll just play some of it and see, if he says anything that I can grab hold of.
really is that essential. When we talk about frictional forces and motion.
All right, so frictional forces. Again, this is a physics thing, right? I mean, so I did do one of the videos on friction just because this is so wrong to think of friction as a force. When friction, you don't call the pins sitting there waiting to get knocked over by the bowling ball, you don't call them a force. You don't say they have a force, they're going to apply a force, they're going to do any of that crap. All right, they're just sitting there, and now you're going to change what they are, and the change is going to be completely you changing them by giving them the properties that the ball has. The pins aren't, they're clearly going to exchange what they have too, in the sense of they have nothing. So, but it's, to call that an active thing when it's a passive thing, I guess is what I'm saying, is just wrong. It's just wrong to say. I mean, to say that there's any other action than the one action. You have $10, you give away $5. That's the action. There's no counter action that made you $5 poorer. The action of giving away the $5 is the only action there was.
Through space and spacecraft and even later on
So we know that spacecraft don't obey mv squared, so it has nothing to do with kinetic energy. Kinetic energy won't move anything anywhere in space. That's just an absolute fact ever. You'll never, calculating kinetic energy will get you absolutely nowhere in understanding motion in the universe out there.
Kinetic forces. Anything involving a force, when you want to figure out how that force influences something to move, Newton's second law of motion, it comes into play.
Right, and it's his second law is that twice the motion, twice the force, twice the motion, 3 times the force, 3 times the motion.
So, no pressure here, but it is that important. I encourage you to watch this a few times. Now, the good news is I'm going to explain it to you in a way that you'll understand it in your bones. You'll know
whatever.
what Newton's law actually is, hopefully give you some additional insights along the way that maybe you won't get out of a standard textbook somewhere.
Yeah, well, that ain't going to happen. From what I remember anyway, it ain't going to happen. Okay, so yeah, there's nothing else in the comments.
Now remember, the number one thing we talked about in Newton's first law of motion, as I tried to beat it into your head, that forces do not cause motion.
All right, so this is right where we're saying, okay, so what is your proof of that? Forces don't cause motion? I mean, yeah, they do. So, the argument that force is something carried by matter shouldn't be that complicated, right? I mean, arguing that it seems kind of obvious that the force interacts, the force doesn't just die and disappear. It stays in the object and continues to move with the object until the object encounters something else, and then the force moves. So it's like a possessing demon. It's just so obvious, in my opinion. It's just obvious. I just don't know how. This is a fundamental elemental notion in physics, and it just means, it really should be fairly argued, and they should show real proof for why they believe what they believe. But the idea, that everything most of the stuff we call a force, as in is the stuff moving the speed of light. That's usually how you argue for forces interacting with something. So gravity moves the speed of light, the electricity, even magnetism, all of these things have that speed thing in common. So the speed of light is essentially, you could argue, the speed of force, because all the forces share that speed. And it just seems so obvious that you have this stuff, the force, and clearly when the matter is exposed to a differential in that force, it acquires, that differential. And so it does, in fact, stick to it. It's in it. It has it. And then it has it until it loses it to something else. And It can lose it to more little tiny matter bits in the case of friction, or it can lose it directly back into speed of light stuff. But it clearly moves through the universe. So again, this is Descartes. Have they fairly argued Descartesian physics in the sense that the energy in the universe is fixed and constant? You can't change it. It's just always been somewhere. So they will concede that you're breathing the same air that the same molecules of oxygen that the dinosaurs were breathing. So they'll often recognize how the system works, that all of this stuff is recycled, and essentially the truth is that the force is also recycled. It's just constantly moving through this thermodynamic heat cycle where, if the movement is divergent, many directions, you call it heat or waste, and when it's in one direction, then you call it capable of doing work, and you call it power, and you call it lots of things. But it's really the same thing. It's momentum when it's in little pieces, it's momentum when it's in big pieces, and it's actually momentum when it's a force. Because it will cause motion. Shit. Yeah, not complicated. Really not complicated. I just don't... 10 years and I can't get anybody to rationally respond to that argument. I mean, what is their argument? The force bangs into it and stops moving or something, and it gives the other object movement, but the movement is just movement. It's not made out of anything mechanical. I mean, you can understand there's forces between the electrons and protons. That's why they don't, that's why they behave in a way. It's because they're communicating with each other based on a speed of light force. The electrons are in speed of light communication with each other. And when you push on one, you end up at the speed of light pushing on the other. I mean, it's just so obvious that there's force controlling the subatomic parts.
In other words, objects move in deep space in a straight line without any force. What actually...
So, again, that didn't make any sense, right? Objects move in a straight line without any force. Obviously, they had to have a force. The Earth was pushed into its orbit. It was hit by things that makes it move. It's just kind of ridiculous to say things move without being acted on by a force at some point in their history. So that's just a fact.
Happens is forces cause motion to change.
So again, they cause it through a process, and it would be silly to say the process doesn't involve absorption. And every single experiment sort of just shows that every contact between two material bodies will involve absorptions. They will start to absorb each other's condition. They will communicate that condition and absorb it.
So if an object's at rest and I push it, it changes its motion. It starts moving.
Yes, that's the only part we agree on, that it's a change in its momentum, a change in its motion, and Newton's argument is it's completely proportional. Twice the force, twice the motion.
If an object is already moving in a straight line, and I push on it, then I change its motion to speed up or slow down, or to change directions. So,
right, so changing direction's a little tricky, because there are places where you can do that where from the observational point of view you're not going to see how that was accomplished and what energy was used to make it happen. And it may appear like it wasn't any energy. And the fact is that in some cases it's like saying there wasn't any, because you'll never see the diminishment of the condition. So it's like the tiny grain of sand bouncing off Pluto or something. Okay, the capacity of Pluto to reflect the grain of sand is almost infinitesimal. Infinite compared to the motion of the grain of sand. So the fact that it gave away, it used some of its condition was exchanged to create the new direction. So you could argue that gravity on a racetrack, right? Okay, so if I tilt the road, if I don't tilt the road, the cars have to use their own energy to create the curve. So they have to create more friction, they have to create a lot of, waste energy. They have to give away a lot of energy to do the turning of their direction. So they have to use their energy, so they have to slow down. But if you lift the track, then gravity provides the turning energy. It does the pushing. It does the conversion of, adding force to bend the path, and therefore the car can maintain its velocity because it doesn't have to waste its velocity creating the change in the direction. So clearly you can argue that if some other force applies the turning energy, you don't have to apply it. And that's what gravity does to keep things in orbit. It supplies the turning energy, so the orbital speed stays the same because the turning energy is being applied by gravity.
Forces actually cause an object to change its motion. But what is a change in motion?
Yes, it's a change in the momentum. That's exactly what Newton draws. So let's just say this is, they've broken Newton's concept in the sense they've written this F equals ma crap. And what Newton wrote was E. Oh, no, he wrote F, sorry. Yeah, he didn't know what energy was yet. They didn't have the word energy. Force equals the change in your momentum over a period of time if you want it in a rate. So obviously Newton was working with gravity, a lot of things that were going to be at rate. So like 9.8 meters per second over 1 second. So I don't fuck you, I don't want any of this crap. God, everything has to be ruined by Google. Anyway, and so it's so it's in a rate, all right, because you're saying, well, how is it, these are forces that are kind of aggressive, and so they're constant and that kind of thing, but there's plenty of forces that are just instantaneous. They're just net forces. So what physics often does is it likes to say that this is the net formula, and of course it's not, because there's no such thing as the net time. Okay, it wouldn't be any point. You just get rid of it, and so the net force is the net change in your momentum, and that's Newton's conceptual. This one's no good. Oh, threw it out and it didn't get all the way to the Hey, that's pretty funny. Yeah, slides down the back of the chair instead. Alright, so we need a different pen. It's good for testing pens. So that's all. So this is clearly what Newton was saying when he said twice the motion is created by twice the force, 3 times the motion, 3 times the force. Clear equality between the effect of the force and the change in the momentum. Those things will be the same. And they've perverted it by using this F equals ma to eventually get to a point where they're going to say it's the acceleration squared equals the force, and it's not. That's a perversion of the truth. It's a lie. They can read the sentence under the second law. They can know that it's not Leibnizian physics. It's not mv squared. It's mass times velocity, period. That's Newton's physics.
A change in motion is an acceleration. So what we're saying is that...
Oh, I have to put that back. All right, let's see. We have another sentence here by the commenter with a little crown. I've been wondering if the history that made mv and mv squared what it is now understood by physics. Like, do they even know Leibniz or vis vis? Well, it's scary that obviously I can science that. Obviously that guy doesn't know any of the history. But yeah, it's a really, it's not that I mean, vis visa even is such a strange word, and they were still using this. Lord Kelvin was using that word. Joule was still using vis viva. So they were still talking about this living force, you know, and it's and the history just proves that it was an idea completely and resoundingly defeated while Newton was alive, and then people got lazy, and it's, you know, it's almost, you could almost say that physics lost its way because it didn't have an icon anymore, you know, it didn't have a Newton to follow. And so everything just went sideways, and everybody started just making shit up. And so then the Chardonnay showed up, and the guy she got the clay experiment from was a guy searching for perpetual motion. And then curiosity is Du Chardonnay herself, she was actually tutored by a Leibnizian, which was kind of bizarre because there really weren't too many of them, right? There was a very rare philosophical perspective. And he actually got pissed off because she plagiarized his teachings, and you know, so he had to sue her for a copyright violation. So the whole thing, the story is, you know, it just makes it just so. And you're saying, and then all the physicists, I mean, really, all of them. I can't find one critique of de Chardonnay's clay experiment. So it's not a single physicist could just make the simple argument that denting the surface of clay is not a valid experiment. And I guess part of it is they didn't do the experiment themselves, and so they didn't realize that the guy was just denting the surface, that he wasn't letting the round objects penetrate the clay. And it just, yes, of course, the living force sounds so bad. I mean, that's just so religiously weirdy, okay? And then you listen to the rest of what Leibniz believed, and you're just, it should scare a scientist to death, you know, because he was so obsessed with his religious framing. You know, where Newton, everybody finds out that Newton was a bit of a religious kook and was into all kinds of crappy theories, and, you know, wasted half his life, you know, immersed in the Bible. But you wouldn't see any evidence of that in Newton's physics and the science and the experiments, where Leibniz, you know, wrote his God on top of his ideas. And it's obvious and visible. But you can't make any sense out of writings by Leibniz. I mean, he has a book called Monology or something, and it's psycho shit. I mean, it's so fucking loop-de-doo crazy. Just amazing, frankly. How did this happen to physics? I mean, how did they let this happen? Where they let a religious kook define a fundamental, you know, cornerstone of their physics. He's just saying right now, you know, this second law, and the second law, as physicists know it, is Leibniz's law. It's not Newton's physics, it's Leibniz's physics. And they've let that become the cornerstone of their physics. And it's just so damn ignorant.
Forces cause acceleration. That's what we learned.
What they cause is a change in velocity. So again, an acceleration is just changing a velocity. So the thing that is the reality is the velocity. There's technically no such thing as an acceleration. There's things that affect velocity. There's not things that that affect acceleration. You have to change the velocity to even have something called an acceleration. You can't measure it or know it's there. You can't see it unless you first see the velocity change. So again, it's creating some new concept that there's such a thing as an acceleration or an accelerator, when all there is an applied force. Changing a velocity. Twice the force, twice the motion, 3 times the force, 3 times the motion. No squared function.
Before, forces cause acceleration. Newton's second law of motion, it writes this down in a mathematical way. So
again, lie. Because the mathematical way is as simple as just saying force equals the change in your momentum. And that's what it is. That's his mathematical statement.
Talk about it. Newton's second
I hate when they
law
do this shit. Writing
motion.
on a board.
The first law of motion was more of like an object
Draw on a board. Don't write on a board.
at rest tends to stay in rest, an object in motion tends to stay in motion unless you push on it with a force. Newton's second law is the following. The force that you apply to an object is a vector quantity, and it's...
All right, so there's no such thing as a non-vector quantity. So again, even this concept, how do people fall for this? Well, what do you think? What's the non-vector quantity that could possibly exist in the elemental universe? You've done all this Planck stuff. You know that everything's in discrete bits. Einstein gave you these, the word quantum. He gave you a capacity to understand it that way, that there's bits of this thing, this energy, this motion, and so it all has to be a vector. And you're just saying there's things like schools of fish that have lots of vectors in them, all right, and they have a net motion because you just add the vectors. You just figure out where all the vectors are going, do the superficial cancellation. And, there's no cancellation of the energy. There's only a cancellation of the effect. So cancellation is a legitimate word in terms of canceling an effect, but you can't cancel the energy itself. You can't make free energy, and you can't cancel energy out of existence.
Equal to the mass of the object multiplied by the acceleration that the...
All right, so again, that's not Newton's formula. So again, they just keep putting Newton's name. He says it right there, Newton's second law. That's not his second law. That's not what he wrote. That's not what he conceptually understood it as. So it's a distortion of the truth. Now, it would be okay if they meant acceleration was just net acceleration, or if they or if they recognize the fact that it's a time-dependent, a rate of acceleration per second, then it would be okay. But they're going to say it's seconds over seconds and call that second squared. And that's where it all breaks down.
Object has. F equals ma. Now I'm putting the...
So obviously Newton's formula would have just been F equals the change in mv. That's Newton's formula. So they're just lying about one of the greatest scientists in human history. They're distorting what he said. They're perverting it.
Vector arrowheads on top to remind you that the force...
There's no other choice. I mean, what other way could anything be? How can something be a non-vector of motion, a non-vector of force? You can't have a non-vector of force. Even a flywheel at any one moment has real mass moving real vectors. There's no such thing as non-vectored energy in the universe. There's no concept of what non-vectored energy would be.
As a vector, it has a direction, and the acceleration is also a vector. It has a direction. The mass of an object is just how many kilograms it has, so there's no vector associated with...
So, and understanding the mass is the carrier. So if you take a force, you could argue the force is also a carrier of force in the sense that, they claim that photons are massless, and they just claim it. They have no good reason to believe they're massless because they do in fact impose momentum. They exchange it in a sense, and there's just no reason to think they're not momentum carriers. They have mass and a velocity. But regardless, the fact is that mass carries force. You can give a dead mass, a dead electron, a dead proton, you can give it motion by exposing it to force and having that force essentially stick to it and move it. So, yeah, I guess I might as well throw it in here. I mean, this is going to be a lot of redundant stuff, so it shouldn't scare you too much that, oh, he's going to be redundant. He's going to say things he said before. Oh, no. Well, I was kind of hoping that would erase. Yeah, that would have been nice. Let's see. Yeah, I did find some new stuff that erases even better than my old stuff, but I don't know where I put it because I cleaned off my desk a little. I actually have a keyboard on the desk now, but obviously I haven't found a place for the mouse yet. See, this is where the mouse traditionally is. It's here. And it doesn't work on the whiteboards. That's why I have to put something else on it. And obviously when I'm making a video, there's no place for the mouse. So we have these kind of little tragedies. Alright, so what the fuck was I going to talk about? Let's see, force, the Sisyphus argument. Yeah, so, I mean, you know, it's just such a basic argument, but you could just understand that the force could just be understood as Sisyphuses. They're the things that have the pushing power. And the electrons and protons are boulders. And so when the Sisyphus is flying free, he's going 3 million meters per second, right? Okay. When he's pushing... when there's one of them pushing a boulder, you could argue that maybe he's only going, I don't know, 100,000 meters per second. Okay, so the boulder is like 30 times lighter or 600 times lighter or some amount. And the fact is that so now the force, the Sisyphus, isn't going to get where he was going at the same time because he's now pushing the heavier bit of matter and moving slower. So it's like you picking up, like say if there were giant dragonflies still, and you were driving your car and you plowed into them and they were all sticking to your car, making it heavier and heavier. You won't get home at the same time. Alright, and so you could have a whole bunch of Sisyphuses, okay, because you got hit by a laser beam or something. And so there's a greater amount of them coming one way or the other way, and you can only move in one direction. You can't move in both, so they can't stick both ways. So like a Newton's cradle, you know, you hit from one side and that one pops off, you know, and this one reflects. That kind of thing happens. So they can only go in one way. You can't store up a whole bunch of them pushing both sides of the boulder. That can't happen. So anyway, so if you have a net force that's greater on this side and weaker on this side, then you can understand that it's going to collect the Sisyphuses and move in that direction, and that's the constant force like gravity or something like that, where you're in a net differential. It's a constant differential, and you'll just keep collecting Sisyphuses based on your length of time you're in that differential, and you'll go faster and faster because you're collecting more and more Sisyphuses over time. And then when you hit the ground, the Sisyphuses will jump to other objects. Boom, boom, boom. You know, and you'll dissipate your Sisyphuses. That simple model works. And because of the change in the time, you know, how the force is slowed down pushing matter, it explains why light slows down in glass. It explains why electricity doesn't move quite the speed of light in a wire. It explains so much, you know, the obvious one, which is gravity. It explains why you're in a force differential, because the force coming from space, the Sisyphus is hitting you, the raw ones, and then you have the ones that had to go through the earth and push boulders to get to you. Obviously, they're going to show up a little bit late, and so you're going to end up in a force differential. I mean, it explains so much, and it's so simple, and you can't get a physicist to explain why this can't be true, because there aren't any experiments that prove this can't be true. It's just so annoying. It's beyond this planet. I mean, it's just so obnoxious that science is so closed. They will not be challenged. Ugh.
The mass, okay? Now, before we actually talk about this, let's write down the units of it.
I mean, you challenge them and they'll start to, you know, deface your penis. They're that petty.
This thing. Now, the force that we're talking about is always measured in newtons. The mass of the object is always measured.
We all know all this measurement shit is just arbitrary. So, okay, the kilogram's decent enough, but obviously you could use pounds. You can use anything You just change the number, right? So 1 kilogram is 2 point whatever it is, 4 pounds. So you can replace this with anything you want. And as long as you make all the same replacements, it works fine. So this is all quite bullshit. This idea of putting it in these strange quantities when all it is a weight. All it is, can be converted directly into pounds, or it can be directly converted into joules or watts.
In kilograms, not grams, kilograms, and the acceleration.
So we know, again, these aren't Newton's numbers because Newton was using pounds and miles per hour, I think. Yards, feet per second. Yeah, maybe that's it. Yeah. It was 36 feet per second is what Newton, 9.8 meters was 34, 36, 32. One of those numbers.
Is measured in meters per second squared.
All right, so there's no squaring of the seconds. It's just absolute crap. What is it there for? There's no reason to say there's a squared second. Why is it there? Because they say this is per second. That's why it's there. So they say to write per second, that is, you could have any number of seconds worth of the force, that somehow you square the second. But they also know that their mathematical notation takes that square seriously. It doesn't think it's a fake square. The math thinks it's a real square, that you're actually squaring the value that they're going to put in for acceleration. So they put the value in for acceleration and they square it when no, it's not supposed to be squared. It can be 1 second, 2 seconds, 3 seconds. It can be any number of seconds. It's not squared number of seconds. So it's just such nonsense.
Right? And that's very, very important. So when
it's very, very corrupting of logic and meaning.
whenever you are calculating,
I mean, we know the change in the velocity is a velocity number. And we know it's not seconds squared. We know it's a meter in meters per second. You go 60 miles per hour. You go 60 meters per second. There's no square. That's the change, 60 meters per second. There's no square.
something in terms of forces and accelerations and things like that, keep your accelerations in meters per second squared.
It's not squared. So why would you do that? I'm just saying, if you were going to say there's a velocity and you're going to talk about changing the velocity, it would only be in meters per units of time, a 1 second unit of time. There's no point in having the formula if it's 7.4896810. You wouldn't bother saying 60 miles per 0.7168684444 miles. You wouldn't do that, or hours even. So it's supposed to be meters per 1 second. That's what the velocity is in. Just as it's 1 hour, 1 meter, 1 second. It's one of them, not units squared. Not even 1 squared. 1 squared is still stupid.
Keep your masses in kilograms. If you have some other unit like grams, change them into kilograms. And when you do that, then the forces will always be in newtons, right? And remember, a newton, as we talked about before, is roughly the force that you will feel from an average apple. When you hold an apple in your hand, that's about a newton.
100 grams. Yeah, that doesn't sound right, frankly. No, the weight is a kilogram, so the average apple doesn't weigh anything like a kilogram. So that doesn't make any sense. I mean, a newton is the impact. A joule is the impact of, so a joule weighs a kilogram and a newton weighs 100 grams. Yeah. Simple enough.
It's pretty close to a quarter of a pound if you like using pounds, but
yeah, that's right. So so he's using pounds, and again, there's 2 pounds, so it's the whole thing that a kilogram is like 100, is like 1,000, is a kilogram is. So he said a quarter pound. You could understand if you did 1/5 of a pound, then that would, a quarter would mean that you have 2 full pounds inside of a kilogram. So now you have 1/8. Now you have 8/8. And you're just saying you could add the extra couple of things by just saying it's a little bit more than a quarter.
Of course, I don't like using pounds, but some people need that in the beginning. It's about the force you feel in an Earth gravity of an apple sitting in your hand, a typical medium apple.
Right, so that's a Newton, 100 grams. So apple's way more than that.
What does this equation mean? This means that if I know how much something is accelerating, I can measure its acceleration.
Quarter pound, right, so a quarter pound is like 1/10 of a kilogram. That still isn't making any sense. So a quarter pound, yeah, you're still stuck. A quarter pound is 1/10 of a kilogram. That's 100 grams. Apple's way more than that.
And I know how much mass that object contains. By multiplying these two, it tells me how much force I must be pushing with.
So we know we don't multiply any meters second squared. We know we just multiply a mass times a velocity change, and that'll be the net force. So what's the total change in the velocity? That'll be the net force. What's the rate of change? Well, that will be the net force. That will be the mv divided by the number of seconds.
To cause that acceleration. Because remember...
times the number of seconds. Sorry.
Things only accelerate when there's some sort of force somewhere. Only. I'll say it again. Things only accelerate. They don't accelerate for...
All right, so force is either because some piece of matter carries the force, or because the force, radiation of some kind, hits you directly. So you can get hit with Sisyphuses directly, or you can get hit with boulders that Sisyphuses are pushing. So that's an important distinction.
No reason. You have to have a force. Newton's first law says things want to move in a straight line at a constant velocity.
Well, yeah, the straight thing is obvious. So yeah, I don't even see how anybody, and again, you're arguing that there's some other kind of motion, the non-straight line scalar woo, that nobody, I can't understand how you come up with or contrive this nonsense. So the word scalar wasn't invented by Newton or Leibniz. It wasn't a real concept until the 1800s when somebody used it. But it's obviously just crap. There's no such thing as a scalar energy. All right, I'll take a little brief smoke here and look over the comments. Let's see if we got anything new. All right. Hey, Gary, do you agree with Newton's interpretation of the white light through prism experiment? Well, I certainly agree that the prism, you're changing the angle and changing how much glass it travels through lots of things. So obviously you can separate light out. So I don't think whether you manufacture the colors or whether the colors are in the light is a trick question, I guess I'd say. I can't answer that one. Yeah, so I guess I won't. Okay. For sure. Just because you can think of ways where every time we see a color change, it's because the photon interacted with matter, and the matter could in fact be changing the frequency. So it's not impossible to understand that there is white light that's capable of being changed into any frequency. But yeah, I don't know how hard to push it. The weird thing is metal, right? When metal reflects light, it reflects in this silly gray color. And that one sort of makes you wonder, why isn't it a color? And why is it gray? But I mean, Newton was really clever in the sense that, they say that you have to wait till Maxwell and Hertz to have arguments about the fact that, there was a wider spectrum than just light. And, because Newton had already, that's part of his prism of experiments were proving the fact that there was still heat, that he could detect light you couldn't see that created heat. So he knew the radiation spectrum went both ways. And, that was very clever. Just you can't even imagine doing all these experiments and they haven't even invented running water. I mean, it's just, amazing. 11 kilograms? What are you talking about? A quarter pound is 11 kilograms? I think maybe he says 0.11. Yeah, well, 0.11 would be about right. So that's what I'm arguing. I'm just saying I don't think an apple is 100 grams. Even a quarter, but I guess it's a smaller apple than I'm thinking of. But anyway, it doesn't matter. I just don't think I would bother with that analogy. The quarter pound thing works just because, yes, that's about 100 grams, 106 grams, I think. Quarter pound is like 106 grams. So that's what he just say. It's 100 fucking grams. A Newton is 1/10 of a joule. That's the thing they should, right? I mean, they could say that. They could just say, honestly, yes, a Newton is 1/10 of a joule. And let's quit playing a game that we should be talking about these things like they're different things. They're not different things. So let's not pretend the Newton pressure is different than the joule pressure, because it isn't. It's just that you put the scale in a different condition. You're just saying that the Newton scale is 1/10 of the joule scale. And so all you do is the conversion and say, well, I just multiply a Newton times 10 and I have the joules. No, I'll do the opposite. Right? Yeah, I'll divide the Newton by 10 and have the joule number.
That's no acceleration. If I go into deep space and throw something, it's going to go forever and ever and ever.
So we haven't proven that one, right? So again, it's fine to say that there's no apparent drag, but you could argue that theoretically, there has to be some. So let's say I throw it and it goes through the Crab Nebula, right? We know the nebula is full of all that gassy stuff they take pictures of and make it look all wooey. Like beehives and stuff. Well, we know that if there's a bunch of gases and bullshit, that the wrench will hit that stuff and it will lose momentum. So we know that there are atoms in the universe, and even the most empty space, they already know that there's a certain number of hydrogen atoms that are still moving through that space. And you could argue that even the photons, right, they're going to hit a little bit more light because they're going to head for something that's lighter, and it's going to push into more photons, and so there'll be more photonic pressure against its motion. So it isn't really true that I could throw a wrench to another galaxy and have some expectation that the wrench will still be going the same velocity it was when I threw it, because there's no reasonable possibility of that being true. Kind of a fact.
A straight line with no force applied, no forces. It's just coasting, right?
So, and it's coasting. Why? Because it's possessed. It's got syphicuses stuck inside of it. There's forces inside of it. There's more of the little beasties going this way than that way. Connected with all the electrons and protons. If you add up all the stuff interacting with them, there's more pressure going this way than that way, so it goes that way.
But if I want to accelerate that object, what Newton's second law is telling you, if I want to speed that thing up, I have to apply a force to it. And
so I just have to crash it into something and change its velocity. Or I have to apply more velocity, or I apply a different velocity. Now the interesting one is when you apply a different velocity, because then you end up with a mixture. The dimensions don't add, they combine, okay? And so you end up with a hypotenuse, instead of this much this way, and the same amount going that way, and getting a line that's double the length. You don't get a double length line. But that's just because of the dimensions rub into each other.
Force, which is a pushing force of the rocket engines, is going to be equal to whatever the mass of...
All right, so we know that the force of the rocket engines isn't going to have anything to do with mv squared. So it's not going to have anything to do with that second squared he wrote. That calculation, that second squared joule calculation, will have nothing to do with the how much motion the spacecraft gets. So the spacecraft is only going to collect the momentum of the force, and there'll be no element of any kinetic energy in the rocket ship's motion. So all of the kinetic energy beyond the momentum will in fact do no work.
The object is multiplied by whatever acceleration I want to give it. If I want to speed that thing up, let's say 5 meters per second squared, that's the acceleration.
Per second squared.
Then I multiply by the...
It keeps saying it, and there's no per second squared. That's just not what's happening. There's no squared amount of seconds. It's a rate. It's in 1 second units. There's no squared seconds. It's just so wrong to say it. It's just wrong to say it. You know, they just keep doing it, you know, because they don't pay any attention to the argument. But I mean, it's just so wrong to say the rate is second squared, because the rate has to be in foundational units. It has to be in elemental units. It has to be in a unit, and one of them. If I change the denominator, I have to change the numerator. If I, you know, you can't change one and pretend that you can have the same number on the... I can't put 4 seconds at the bottom and then have the same 9.8 at the top. Continuing.
Mass, and it tells me how many newtons my rocket thruster must push with.
Okay, right. And so he said how many newtons it must push with, and then he's going to come up with an answer in joules. Now, does that make any sense to anybody? No, come on. The force is in Newton, and somehow the output momentum or motion of the object is now in joules? Ridiculous.
So what it does is it relates the pushing of things, or the pulling, the forces.
All right, well, there's no pulling in the universe. So again, this is another elemental thing, right? Physicists won't discuss what exactly would an elemental pull be besides magic. I pulled it with my eye or brain power. You have to touch something to move it. Okay. You have to make contact, and once you make contact, all you can do is push. That's what contact is. It's an aggression. It's a push into something. You can't pull it anywhere. It can only feel a push. It can't feel anything called a pull.
How does the object respond? Because remember, forces don't cause motion. Motion happens automatically.
All right, so the forces, of course, do cause the motion. They're direct players in the motion. The force is being conserved through the motion.
Automatically, in a straight line forever and ever. Forces cause the motion to change, which is what we call acceleration.
So again, it's okay to call that acceleration. It's just not okay to call it second squared, because the acceleration will not be in second squared. It will be in seconds, because it's going to be a velocity. 9.8 meters per second.
Now, that is what you're going to get out of most lessons, most lectures, most books. You know, and I'm not trying to say that I'm like some brilliant person telling you stuff that other books won't have.
All right, exactly. You're just talking the same crap, okay, that physics talks, and there's no concept here. So you haven't said the word scalar yet, but that's why you had to put those lines on there, is because somehow you think there's some other way to represent motion in the universe except for that little fucking arrow. And there's no other way to represent it. Pressure, force, weight, motion, it's all an arrow, a vector.
But what I'm trying to do is I want to focus on what I think things that aren't emphasized as much. Because anybody can take this equation and multiply two numbers together, and we could do our first problem like right now.
Well, go ahead and do that and see what happens with this meters per squared here, this meters second squared problem. Because it's just going to make a mess. Because the output isn't going to be squared joules. Yeah.
But I want to go deeper, because I want you to understand a little subsurface, a little bit deeper layer as to what's happening here.
How dangerous is
Oh, well, that's unpleasant. Well, nothing I can do about it, so you'll just have to endure it.
Chitterelli?
The amount of money they waste. Google just makes all this money on this political hackery crap. Disgusting. Oh, people need a 15-second commercial to decide who to vote for. I mean, why don't they just, call each other ugly? It's just so useless. Oh, shit, I should have gotten around to getting rid of this ad. Sorry, my bad. So more fake healing. Oh, I can cure everything. It's disgusting, these commercials.
Force is equal to mass times acceleration. What it means is that in order to produce an acceleration on some mass, I must push with some force.
Right. 1 unit of force, 1 unit of motion. 2 units of force, 2 units of motion. 3 units of force, 3 units of velocity.
Alternatively, if I apply a force to some object and I know its mass, then I can calculate the acceleration that will result from that force.
The change in the velocity, again. The change in the velocity. And you got to get this understood. There's a net change, like an event takes place, an impulse, and it's just going to be a net event. It's going to be a certain amount of force, a certain change in the velocity, period, and in those cases, the force will always equal the net change in the momentum. It's that simple.
Of pushing or pulling, all right? Now, the vectors that are on top of these things, this is what we call a vector equation. And what it means is that because they're vectors, remember, a vector is a number, a magnitude, and also a direction.
So we know that you could just say, frankly, that you can represent it as a magnitude, but it's the fact is it's what you're going to put into the object, and that it all has to be conserved. So I could just say it's a number like 4 or 7 quanta. I don't have to represent it as a length. I can represent it as a quantity. I mean, you could argue that you're getting hit by 9.8 units of gravity per second, and they're just clumps. And you say one clump has 1,000,000 photon power or some kind of number like that. But you can just reduce it to some idea of clumps of capacity, clumps of energy, and clumps of matter.
And because the acceleration has a vector and the force has a vector, both sides of the equal sign, what it means is that the force must be in the same direction as the acceleration. That makes sense. If there's an object here in space and I push this direction,
So again, we know that the fact is you could be slowing something down, not speeding something up, and all of that. So I don't know. I mean, obviously the condition of the other object will tell you whether you're opposing a force, reducing it, or increasing it.
Expect it to accelerate in the same direction. The vector...
You're going to exchange your force and give it to the object. That's all you can do, is it make exchanges. Energy is a currency. You can just exchange it.
arrowheads mean that the force and the acceleration always, 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 always have to be in the same direction.
So I don't know. Obviously, a deceleration isn't in the same direction, but who cares? I don't want to argue with him, but it's just not quite right to say always in the same direction as what?
Always. That little nugget right there will save you a lot of time in many problems.
Yeah, I don't see how it does. I mean, it's just so obvious you're just going to add arrows. So once you understand that you're going to put this vector on that vector on this vector and end up with a line, and that's going to tell you your net effect. So it's not that complicated. If I have a line going this way and I put the tail of the other one on top of it, and I have two lines of the same size, well, then I'll know I have a net nothing. I won't change anything.
Because sometimes you're not sure which way the acceleration should go, but you'll have some forces, and then you remember, oh wait, Jason said the force and the acceleration, they always have to be in the same direction. Why? Because this is an equal sign. And that means that the multiplication has to equal to the number of newtons, sure, but the direction over here has to be the same as the direction here because this is a vector.
So again, it really doesn't make much sense to me to say it that way. I mean, obviously, it's still going to be who's got the bigger arrow. It's still going to be a tug of war. You're still going to be in a circumstance where the change can be equal in both objects. Like the Newton's cradle again. You know, when they both crash into each other, what really happens? Do they both reflect, or is the energy just passing right in going this way and the other energy is just passing right through the other one? So the arrows just go right through each other. You can look at it either way.
Equation. So now we're growing up a little bit, right? In like 6th grade, you learn how to write an equation. You know, y equals 3x plus 4. That's
boring.
That's just an equation with numbers. Put numbers in, and you have to have the same numbers on both sides. And now we're growing up a little bit. We're in physics. And now we have a vector equation. And that means that the numbers you multiply have to equal the force. But since it's a vector, the direction here has to be the direction of the force. That's what the vector arrowheads on both sides mean. Because when I first...
All right, but you're really not going to multiply the vectors. You're going to add the vectors. So I don't really get that one either. What vector am I going to multiply? I'm going to multiply the mass times the change in the velocity, but I'm not going to. The mass doesn't have a vector, so again, I don't think he's being as clear as it could be.
learn physics, I kind of ignored the vector arrowheads. I didn't even write them half the time because I didn't care. I just thought, well, I'm calculating the force. But it's very important to know that the force and the acceleration are lined up. So what does this mean? Let's take a couple of examples, because this is just a general equation. But now let's say that I give you a force which exists only in the x direction. Then what it means is it's equal to the mass times the acceleration, which happens in the x direction. So this is a component in the x direction of the Newton's second law. And we also now know that the force which is pushing in the y direction is equal to the mass times the acceleration that happens in the y direction. Now you see how we're starting to break it into components. We learned in the past that we can break forces into x and y components. Why? Because then we can treat the x component as its own equation, find the acceleration in the x direction.
So all that's unnecessary, right? Because when two things hit each other, they're not going to be hitting each other with their components. They're only going to have one velocity. So let's say I launch something off a cliff and it's running a parabola. Well, the fact is when it hits the ground, it's only going to have one vector of motion. Yeah, we understand that the force of gravity created the vector going this way, and we know the original velocity is going that way, but the combined velocity now exists. The fact is it has more momentum than it started with, because the gravity has added momentum in this direction and it has a new vector. So it's not like you can add those two numbers. You have to add the two vectors to come up with the new length or the new magnitude of the vector. But clearly it's a one-dimensional vector. All the motions are one-dimensional. There's no x, y components in reality.
direction. We can use the force that's in the y direction component and get the y version, or the y amount of the acceleration. So to draw a few pictures here, let's say we have some block with a mass m. And this is the x direction here. So let's say I push to the right in the x direction. This is now purely in the x direction. I push on some box of mass m, and it's going to produce some acceleration in the x direction. The force and the acceleration are in the same direction, right?
Last question. If you could pass one piece of legislation.
So he's going to mess it up because he's going to, instead of just saying, okay, you're in space, you push something, what's it going to do? Yeah, it's going to move completely proportional to the momentum of the force. The value of the force, the pressure, the weight is going to be exactly what you're going to end up in the byproduct. Yeah, selling. You got to survive the nuclear bomb. It's just a scary world, frankly. Survivalist.
Block, and I push upward in the y direction. Well, what it's telling me is that the acceleration is the acceleration a sub y is going to happen in the y direction. So the force is equal to mass times acceleration exists in the y direction, and the force and the acceleration are lined up in the same direction. The force and the acceleration in the x direction are lined up in the same way. So if you now broaden yourself and say, well, what happens if I'm not pushing in the x or the y direction? Let's say I'm pushing on this corner at some angle.
So we know none of this means anything, right? Because gravity is obviously pushing you from all kinds of vectors. Okay, there's all kinds of vectors that are hitting you and pushing you. And the thing is that all the vectors this way and this way end up combining to produce this way. So all you have is a vector down because all the other vectors combine to create down.
And now I'm not going to put x or y here because it's just some vector, it's some oblique direction. It's not really purely in x or purely in y. But what you do know.
So you can try to break any motion and say it has these components, but it doesn't actually have them. They're arbitrarily created. They're synthetic. They're not real because the forces instantly combine. They instantly turn this, a force this way and a force this way, they instantly turn into a force this way.
Is that the force and the acceleration have to be lined up. So these two vectors are lined up in the same direction. When you read force is equal to mass times acceleration with vector arrowheads, it means the directions are the same too. Now, in real life...
So again, none of this. The most fundamental thing of Newton's saying in the second law is the motion part. 1 unit of force, 1 unit of motion, 2 units of force, 2 units of motion. And he's ignored all of that and started with doing multi-dimensional force vector addition. Because that's what it's going to end up being, right? I mean, it can't be going anywhere else here in the sense that he's just going to combine a frictional force. He's going to add some other force to say there's some reason why we have to add vectors now.
If I was pushing on this block with some force at some angle, I would break this force into a vertical and a horizontal component. And then I would calculate the vertical.
And we know that if you apply the force at the non-center of its mass, then that's also going to have an effect in the sense that yes, you're going to have a component going straight, and then you're going to have a component because it's off the mass that's going to be in some other turning direction, some torque. So you're going to start spinning the object.
And the horizontal component of the acceleration, which would reproduce what is happening here. But still, I just want to show you the force and the acceleration in all of these cases are in the same direction. So now let me get a little philosophical and tell you some insights that you may or may not read in a book. You can see that force is equal to mass times acceleration. We now know that force and acceleration are both vectors. They're both in the same direction in all of our pictures, but the length of the arrows might be different because, of course, when I multiply...
Right. I mean, the force can be a deceleration. So again, we're talking about a change in velocity is a better term to use, right? Because the change in velocity can be up or down. So stick to that, unless you're going to be clear that you're talking about an acceleration. See, the arrow can't be in both directions. It needs to be an arrow in both directions, signifying the fact that it could be a deceleration that you're causing.
By these, I'm going to get a new number over here, and so the length of the arrow might be bigger or smaller for force, but the directions will be the same. So basically, the force is a vector arrow in one direction. The acceleration is a vector arrow in the same direction. The only
So again, there's no way to do these equations. This is like having a single object gravity equation, right, where you just have the moon and there's nothing else. Well, gravity becomes irrelevant. I mean, this formula becomes irrelevant when you're not going to talk about the object you're in contact with. Having the force and having motion only means something because of the contact it creates. So he's basically saying this is just an idealization where the object isn't moving and you apply a force. Because in all other circumstances where the object's already moving, this isn't going to be true. I mean, it's not going to be true in the sense that the end result can still be a vector in the opposite direction. You only slowed it down. You didn't reverse its direction.
difference between the two vectors, other than what they represent, is the length of the arrow. So what you can say is that the force in this equation and the acceleration in this equation, they're basically related to each other by a conversion factor. The conversion factor is what we call the mass of the object, right?
So the carrier. Yeah. So again, they don't really do the force thing where they should say the elemental force is obviously moving the speed of light because that's what all the elemental forces are doing. And when the force is in the form of matter, it can be moving all kinds of speeds, different kinds of speeds.
So the mass here, it's telling us how much influence the force has to produce an acceleration.
All right, so this really, he really should do masses against masses and just say the force also can affect as if it was a mass. So just do the MVs against the MVs and recognize that as you're either going to add to something's velocity or subtract from it when you share your conditions. So yeah, I just think it's a very poor way to word it. But whatever. Alright, nothing new in the comments, so play some more.
In other words, remember the concept of inertia.
No. So again, just another word they made up for no reason. There's no such thing as a resistance to motion. So I'd argue that Newton was poorly articulating a concept if he actually said resistance to motion. Who knows what the Latin really said. But clearly nothing resists being moved. You have to move it. You have to apply the force. If you don't apply the force, then it's not going to change and it's not going to move. So it's that simple. There's nothing resisting. Homeless people do not resist being rich people. Give them money and they'll take it and be rich. So it's just wrong to say there's any resistance. It's just a fact that to move matter, you have to move its mass. And if it has a lot of mass, you need a lot of force to do it.
We said we go into deep space and we have a very massive object like a car, like an automobile. If we push on it with 1 Newton, it's going to move, but it's not going to accelerate very much because it has a high inertia, right? So if I have
So we know that if you push on it, it's not going to move at all. You're going to move. So unless you're standing or you're on the space shuttle and you're on the little army thing and then you push on it, well then you got a chance because then you're tied to a much larger mass who's not going to want to change because it's already going in a direction and doing its thing. And to change its direction means you have to change all of its atoms. Every single electron and proton has to be persuaded to move. And if you aren't applying enough energy to move all the atoms, you're not going to move. That would be my argument, okay, is that's why things reflect. Things reflect because the energy can't be absorbed by an object. This is another concept that physics totally ignores. again, they won't have this conversation. You can't force them to have a conversation about what actually happens in the reality. And, they'll claim, because of Leibniz, that you push on something and twice the force goes into the object you pushed on. And, I could have wiped that off without the spray. Well, anyway. And I'd argue that's ridiculous. So, but clearly, this is an experiment done by Bruce Yearney, and I didn't do any frame rates, and I didn't do any of that bullshit. But it's just this simple idea that you tie a rubber band to cars, all right, and you have the same expansion of the rubber band. Okay, so you can either expand the rubber band and then let it crash into the wall, or expand the rubber band, let the two blocks crash into each other. And the truth is that these velocities will be different. That this will be going half the velocity and half the velocity that this will go. This will be one velocity. It will be twice as fast hitting the wall. And it's just logical. You can understand you have to, both of these objects are going to be moving. They have to move at half the speed. There's no other options there to conserve the momentum or the force inside the rubber band. And their argument is somehow that twice that every time you hit something, there's twice the energy in it. So, but obviously you can't say that this moved with half the force, that somehow I moved the whole Earth, that somehow this got half the energy. It couldn't have gotten half the energy if I have a full unit of velocity. I have twice the velocity here. I have the full velocity. And in this case, I only have half the velocity. So just understanding the blocks moving twice the speed here. Obviously, the difference is this side didn't accept any of the motion. This brick wall didn't move. The 500-pound anvil didn't move. It didn't go anywhere. It didn't accept half the motion and take it and go with it. So, their idea that happens is just wrong. And again, they take it this step further where they say, you throw a tennis ball at a wall and it has, let's say, 100 momentums, and the 200 momentums go into the wall, even though the wall doesn't move. And yet I get all of my energy back. I get 100 back. Let's say if it's a really an elastic, more elastic than a tennis ball. Like if this was an anvil and this was a steel ball, a hardened steel anvil. Their argument is every time this ball hits, let's say I made a pendulum. I guess I should make this the next short video because it's such a good argument. Every single time, so it just keeps bouncing back and forth, and it diminishes over time. So but it could bounce 250 times, right? That's the record or whatever, 263 or something. And obviously you put in a vacuum, you get even more, blah, 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 blah. So, but it's a lot of hits, and every time they're saying that the same amount of energy you hit with is the same energy that goes into the object. So you're saying this would keep getting pushed and pushed and pushed and pushed and pushed. So you'd have thousands of times, like 15,000, versus 100 that you started with. You did 100, and you got 15,000 worth of motion in the other object, in the Earth. No, you didn't. Because it didn't absorb it. It didn't accept the energy. It didn't move as it got half the momentum and moved. It didn't get half the momentum. That's why this one's going with 2x. This has twice the momentum of this. Twice the momentum. Okay, so obviously this isn't moving. So that simple concept, they don't even understand what a reflection is. They think a reflection is an absorption, and it's not, put simply. It's not an absorption of your motion. You have to be using some other force, okay, or some other mechanism, but it's this motion, this work, this quantity is not being used to move this. That's why it's going twice as fast. Because it's getting all of the energy from the spring. It's not sharing it with another object. it's just so ridiculous. You know, the whole plus and minus motion is just so ridiculous. Again, they say a nuclear bomb is there's no momentum because it, you know, goes in all directions and it cancels. So there's zero momentum. Yeah. Who believes that? You know, come on, nobody. Too ridiculous. Oh yeah, I move this over so I can just slide it back, right? Yes, that's what you can do. What is this stupid thing doing here? Oh, God.
Very high number here, and I push with the same force, then I'm not going to get very much acceleration. If you think about...
Yeah, if you have a lot of electrons collecting the force, you'll collect lots of force. If you have very few electrons, you'll collect very little. I mean, that's all it's about, is the electrons and the protons. They're the things that actually move first. So there is no event. I don't do anything. I don't say anything. Nothing happens until my electrons and protons, they have to do it first. And then I find out about it, frankly. You know, we're moving so slowly, in our universe compared to the speed at which stuff happens in the real universe where elemental matter exists with elemental force. That universe is where everything happens. There is no law, there is no physics that doesn't happen there. Everything that happens here is a consequence of what happened there. It's the only real universe. This is, composite. This is indirect consequence. The direct universe is just electrons and protons.
Dividing by m, if m is very big, I'm dividing by m, acceleration is very, very low.
It's spooky. Jack Chickarelli says we need to feel some pain.
A lot of those. All these commercials, man, just money, money, money. Wasted.
Off ball, which has a very low mass, and I push on it, it's going to accelerate rapidly. So the mass is the conversion factor. That's, if you think about a conversion factor, what I mean is...
So the mass just slows the Sisyphus down. Sisyphus goes the speed of light, no boulder. Boulder is going to be moving slower. And if there's more Sisyphus pushing, they can get the boulder to go a little bit faster. But the boulder can never go faster than the Sisyphus, obviously. So again, the simple theory explains why nothing's going to go faster than the speed of the Sisyphus, because the boulder can't go faster than Sisyphus. It's just, there's no way to get pushed any faster than the fastest pusher.
Like, you know that...
And again, the pusher's only sharing its energy. It's not giving, it's sharing. It still has to move itself.
There are 100 centimeters in a meter. It's a conversion factor. Meters and centimeters are sort of the same thing, but the 100 is a conversion factor to change one into the other. Or liters to...
Right, so we can change newtons into joules. So why are we using two concepts? Why don't we just say 1/10 of a joule?
Milliliters. Or, I can pick any unit I want to. I can pick a unit of density if I want to. All right? But you're converting between...
Yeah, so why not just have momentum in joules and then quit playing a game like somehow you can pretend that your scalar energy is somehow different than your vector energy? That there's some way to even acknowledge the existence of whatever this scalar crap is. All you're saying is that you have a magical Holy Ghost notion, and the Holy Ghost is in this squared velocity thing, where you say light things going fast, one atom going 1,000 miles an hour has 1,000 times the capacity to push things and break things and move things than 1,000 atoms moving 1 mile an hour. You say it, but it mechanically can't happen, and it mechanically doesn't happen, and you don't have any experiments that prove it happens. Nothing. Zero. Zilch. All right, what do you think of Kurt Vonnegut? Well, it's just so far off the subject, I don't even know what to say. Frankly, I think a lot of writers' stories can be made better, so let me think. I have to think of what this to argue. Let's see, which ones were his? The Fahrenheit 454, was that his? The burning the book thing? Who was that? I just don't. Frankly, my memory is just so bad, so I'm trying to think of what his best novel was. But I mean, I think they're all kind of flawed. Like, I don't think that would ever happen. And I don't think, the plots are all that rational. That you'd bother making a fire department to burn books or something. You would just collect them and throw them in a pile somewhere. You'd have a garbage disposer. You'd have a mechanical chopping machine. I mean, you wouldn't or you'd put them in a furnace and actually use the heat for a good purpose instead of burning houses down. So, I mean, you can find fault with all kinds of sci-fi kind of novels and whatnot, but whatever. Yeah, most of it's just such bullshit. I mean, there aren't movies I'd say I didn't like them, but I hate that they all have pretty gigantic plot flaws in them. Science defects, I mean, they sort of ruined everything. Star Trek got ruined by the silly time travel crap. I mean, it makes for interesting stories, but it is so so incomplete, because there's no way you could even calculate how much you fucked up the past if you even popped into it. How many relationships you ruined, how many things didn't happen in the future because you fucked it up. You couldn't even calculate it. You couldn't even appreciate it until you got back to, like, Homer Simpson did a better job. In The Simpsons, because he went back to the past, and every single time he came back, something was fucked up. And that's the way it would be. Anyway, don't want to get into that conversation. Thanks, but no thank you. See, I just don't think I'm the only person you could ask that question to. See, I only want to be asked questions that I'm the only person that should be asked the question. Because a lot of people could answer the question and say, yes, most sci-fi is just too defective. The premises are not rigorous to actual science.
Between one unit of measure and another. So instead of thinking of forces as like a totally different thing as accelerations, philosophically, you can think of force and acceleration being the same thing.
Right. Force and velocity being the same thing, as Newton stated it. And force and momentum being the same thing is the real point. So as long as you're not changing the mass, obviously the force applied will be the velocity, it will be the mv change. So it really is just to say force becomes momentum, and momentum can become force. I guess that's the important part, is that you can convert from the other way. You can take the mass moving a velocity and you can convert that into a force.
They're both vectors. They're both pointed in the same direction. They just have a different scale factor, and that scale factor comes about because of the mass. The mass.
So that's like the common experience would be that you convert it into the little atoms moving into heat, and then the heat leaves as radiant energies, photons. And so the trick is that you increase the frequency of the energy, the photonic energy hitting something is increased by the vibrations of the electrons and the protons.
Tells us how much influence that force has to produce a change in motion.
Right, so he's doing all this emphasis, and all he has to do is read what Newton wrote right under the second law. Twice the force, twice the motion. 3 times the force, 3 times the motion. I mean, he went so far as to say 3 times to make it clear, okay, it's proportional. 1, 1, 2, 2, 3, 3. Could have gone 4, 4, 5, 5, 6, 6. It's not 25 times the force to get 5 times the velocity. That doesn't happen, and it's not Newton's physics. You people are liars to imply that Newton endorsed that nonsense.
I'll say that again. The mass is a conversion factor that converts from forces to accelerations. And it sort of behaves as a conversion factor that tells us how much influence the force actually has
Right, you already said all that crap.
to produce motion. If I have a very high mass, then a force will not produce much motion. But if I have a very low mass, the force will produce a lot of, I say motion, a lot of acceleration. So that's a little philosophy, but I mean, it's basically what's going on here. These two things are the same direction. That's the critical thing. The mass behaves almost like a conversion.
Well, so as I just pointed out, there's lots of cases where you'll find that the force is applied and it doesn't cause any motion because the force can't move the object because it's too big. It can't move all the electrons and protons. And if everybody doesn't move and nobody moves, that means you didn't absorb the force. So if you're not getting hotter and you're not doing something to disperse the energy, then you can in fact reflect it. It'll go to one end of you, go to the other end and say, I can't get, everybody else isn't going. And so everything just goes back the other way and you get a reflection. The bounce. Because frankly, the atoms are elastic and they can bounce. They can change their direction, right? It's just so obvious. I mean, a bounce is just such an obvious change in direction. And you can do it really efficiently. You can have something bounce really efficiently.
Factor. Now, it's very important for you to realize that when I say force is equal to mass times acceleration, it's really the net force acting on an object. So let's say, for instance, that I have a body with mass m.
So it's really not, right? So again, the word force is used to describe gravity, lots of other things. So obviously the force in photons is going to be at a rate. You know, paint spray going to be at a rate. River flowing, it's going to be at a rate. Wind blowing, it's going to be at a rate. So it's just wrong to say it's always about a net. Obviously, if there's an incident and then the incident is going to be over, then it's net.
And I have lots of forces acting on it. So I have a force like acting right here. I have a force acting here, a force acting here, and like, I don't know, it could even be pulling, some force acting right there. Maybe some force acting right here. So you could do a couple of different things. You could apply each of these forces equal to mass and find out the resulting acceleration separately due to each of these forces. Then you would have all of these different acceleration vectors, and you would have to add the vectors vectorially, and you could get the answer. But what we actually do is we change the problem from all of these different acceleration forces acting on the object. What we really do is we find the vector sum of those forces. And let's just say in this problem, once we add all these vectors up, we do the head to tail and we draw and all that stuff, we figure out that really the force resolves to being something like this. So the sum, this is sigma here, the sum of the forces, or you could call it F sub net. We call it the net force. The net force is what happens when you add vectorially all of these forces together. It behaves as a single force acting here with this amount, right?
Yeah, and that's exactly what it is. It ends up just being the motion will be reflecting the fact that the forces will do this very quick, reaction to each other's existence affecting something, and the real motion will be this net motion. I guess that's all to say. Is the real motion will be the net motion.
Then the acceleration, of course, has to be in the same direction as whatever the net force is. So when we say force is equal to mass times acceleration, if we have multiple forces, we resolve it to a single force, and then, of course, it's equal to mass times acceleration. We get a single acceleration out of it.
So you just, kind of glossed over, but you can't really measure all these forces the way he said because some of them are tangential. They're not going through the center of the mass. So they're not going to, they're simply not going to be the same magnitude. A percentage of that force is going to be wasted turning the mass.
So the way you might see that written in a book is really that the sum of these forces is equal to the mass times acceleration. This is a better version of Newton's law.
So it's only the sum of forces that go through the center of mass. If the force doesn't go through the center of mass, you've got a much more complicated, a much harder problem to solve.
Because what you do is you add up all the forces, and the resultant force, but you're adding them vectorially, The resultant force is what matters to produce the acceleration. Another way you might see it is you might see it as F net is equal to ma.
So again, there's just no point in saying ma if it's going to be meters second squared, because it's not per second anymore. It's not any of that crap. It's a net increase or decrease in your velocity. So it's just deception.
Right? The net force. So what I'm trying to say is when you have multiple forces acting, you resolve it to a single force, and that single force behaves equal to mass time, and you can produce that acceleration there.
Mikey Sherrill, a tough governor.
Ugh, not again. It's going to be bad, I guess, for the next week. Ugh. There really just isn't anything to vote for. It's just so bad. It's just evil and evil. Stupid and fucktarded.
Now, what does it actually mean graphically? I'll do a couple of different things. I'm going to draw some pictures. But what I'll use is my magnet here. Let's say I'm producing a force. This is kind of more like this going here. I'm pushing here. And as the thing starts moving, my force is still being applied. You can imagine it being like a rocket thruster attached.
So again, he's using the rocket example, which is all momentum. Doesn't have anything to do with meters per second squared.
To the object. So as I move it, I'm still pushing it, then it goes faster and faster and faster. I'll go over here. Because the force is still in contact with the object, well, if I can hold it, it goes faster and faster and faster. Because as the thing is moving, the force is still being applied.
I don't know. That was just such a bad example, right? Because obviously the magnet is draining all of the energy into the board constantly by contact.
As long as the force is being applied, the acceleration is still happening. Right? So if I continue...
It's only happening because you're changing the acceleration. So you're not applying a constant force. You're applying increasing force to overcome the friction. So again, this example is just so bad because he has to apply more force to make it go faster and faster. Not the same amount of force because he's not adding velocity to the object. There's no addition of velocity. So it's a really bad illustration of a constant force.
Applying the force throughout the entire time, it's accelerating the whole time. But let's say that I accelerate a little ways and then I just let go of the force, and then the thing is going to go coasting in a constant state of motion.
Yeah, it's right. But it's not going to, like I said, the way you illustrate it is obviously nothing gains any velocity. So you're applying a force, applying a force, applying a force. There's an increase in velocity with every bit of force applied.
So if you have a rocket thruster firing, I'm accelerating the whole time, but then when the rocket cuts off, I'm coasting at a constant.
Yeah, okay, technically. I don't know. I mean, the heat of the metal and the other stuff is still going to radiate a lot of energy, so yeah, you're probably still going to get a little bit of pushing from the residual heat. Let's see what other argument I could make. But yes, you only accelerate while you're giving away something, a force. And that's what you're really doing, is you're giving away a force. Force isn't being applied, you're giving away that way, and it makes you go this way. You're changing what you have to give.
Velocity.
You've put a hole.
And everything starts flowing.
You put a hole in, it's a balloon, frankly. And you can change the direction that you let the force loose in by just changing where the opening is. And so the force is all bouncing around all directions. And the fact is you keep letting stuff go that's going this way. So it would have hit the balloon wall if you didn't let it go. So less stuff is hitting the wall this way than is hitting the wall on the other side that way. And that's the trick. So you can change the direction to any direction, and it just means you're letting energy not hit the wall going that way. Technically, in a way, that's all that's really happening. I mean, it's more complicated because you have a cone and you're expanding a gas inside the cone and forcing the direction into this way, and so you have the tangential vector going the opposite way. But the bottom line is all you're going to get from the thrust is its momentum. You can't get any of the kinetic energy into the rocket.
Floating in deep space because I'm at a constant velocity, an inertial frame of motion. So graphically I can draw this, and I can say here's an object with mass m, and I'm going to apply a constant force to it, and then I'm going to have some velocity.
So, you know, like constant forces for us are very hard to apply. So there's, you know, you can't have a constant force in your car because you have to keep adjusting the force because the thing's moving. So to be a constant force, you have to keep moving with the thing that's moving and applying the same extra amount of push to it. So you have to keep accelerating to maintain a constant force in a car, for example. You couldn't apply a constant force without keep increasing how much you're accelerating.
So I'm going to put a force right here. Now, at some snapshot in time later, I'm applying exactly the same force. Well, what's going to happen? The velocity is going to be bigger than it was. Because force is equal to mass times acceleration. That means that there is an acceleration happening, so the velocity must be getting bigger. So
your force has to go faster. Now, in the case of gravity, it's a speed of light force, so obviously the force is going so fast that it doesn't matter. It doesn't have to go faster. But you've got to understand that if something was moving the speed of light and you tried to push on it with light, the light couldn't push. So it can't go any faster. So if a force has a lot more velocity than you have, then constant is easy. But if it's like wind or something else where the maximum wind is going to be 40 or 50 miles an hour, well, once you're going 40 miles an hour, let's say, the wind is really weak. Now it's only a 10 mile an hour wind. The differential between your speed and the wind speed is only 10. So now your acceleration is going to decrease rather than increase. It's going to take a lot longer to increase by just 1 mile an hour your velocity, where at the beginning when you had a 50 to 0 ratio, it was really easy for the wind to push you, to make you go faster. You were accelerating at, every 1 foot, you would go, 1 mile an hour. And then by the time you're going 40, it's going to be every 20 feet you gain 1 mile an hour.
Acceleration is an arrow represented right here. The arrow for the acceleration is the same length, but it's...
So it's just a change in velocity. So again, it's just a velocity change. So annoying.
Acceleration is making the velocity bigger the whole time. That's what it's basically doing. And then if I go here and do the same thing, I'm still applying my force to the same mass, but now, because I'm still applying that force, that velocity is even bigger.
So again, a constant force is really a buggy physics concept. And the only way we could understand it is the constant force has to be something like a laser beam, something that actually does move at the speed, some preposterously fast speed.
Again, in the same way, and then I have an acceleration there. So acceleration is a vector. I need to put my vector arrowheads.
Ah, brother. So all things are vectors. There's nothing that doesn't need a vector and blah, 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 blah. All right. Well, not much in the comments and probably enough of a video and such. So I think I shall bail. And see you next time and such and all that kind of crap. Yeah. So anyway, just kind of like I said, just a junk video in most respects and such. So yeah, only 7 viewers. Yeah, it's just gotta do better than this and such. Don't know how to do better, but whatever. I can only do my job, right? I can only make my arguments. I can't force anybody to watch them or respond to them. But anyway, till the next time as such. Oh, I don't want to edit. Yeah, that's not very useful. No, thank you. Alright, end stream. That's the one I want.